in the last few lectures we were solving the diffusion equation, which is the Laplace equation or the Poisson equation, okay, diffusion equation. Okay. Del square t is equal to 0, or if you have sources or sinks in the domain, k del square t plus the volumetric source of heat is equal to 0. So far we have considered this volumetric source of heat only as a delta function, where in the limit as the size of the source goes to 0, but the total amount of heat generated per unit time is finite. In that limit we had solved it in a spherical coordinate system. In a spherical coordinate system, using two approaches. One was a separation of variables solution. Okay, if you recall, T is equal to sigma where the terms in this expansion, the orthogonal functions, the spherical harmonics, are all orthogonal to each other. Integral d phi, they satisfy the orthogonality relation, integral 0 to pi sine theta y n m of theta phi. And since these are complex, when I define the inner product, I have to take the complex conjugate of the second term. Is equal to delta n m, sorry, okay, and these are normalized. Okay, so this was the spherical harmonic expansion that we had used. For each value of n, there are two solutions: a growing solution increasing proportional to r power n, and a decaying solution decreasing proportional to 1 over r power n plus 1. So these were the two solutions for the spherical harmonic expansion. The other way of solution that I had shown was by superposing sources and sinks. Okay, so in three-dimensional space, okay, if I have a point source at the origin, it corresponds to the separation of variables solution with n is equal to 0, m is equal to 0. Okay. The decaying harmonics go as, okay, r power minus 1, and the growing harmonic is just a constant, okay, t power infinity, if you recall the temperature, constant temperature far away. Okay. Then I had dipole solutions. Okay. Okay. These were point sources and sinks of equal strength separated by a small distance. Separated by a distance that is much smaller than the location of the observation point. Okay. Okay. In the limit as Lz is small compared to r. Okay. The solutions that you get are dipole solutions with n is equal to 1, m is equal to 0 when the separation is along the x axis, z axis. Okay. Okay. This is for separation along z axis. Z axis. Okay. So, that is for n is equal to 1 and m is equal to 0. The temperature, the decaying harmonic goes as r power minus 2, the growing harmonic goes as r power plus 1. Okay. So, the decaying harmonic is due to a source and a sink separated by an infinitesimal distance. The growing harmonic is due to surfaces far apart that are separated by a large distance. Okay. Surfaces far apart that are separated by a large distance. Okay, that are separated by a large distance, where the flux lines are straight lines. Flux is a constant, temperature increases proportional to 1 over r. Those are the growing harmonics and the decaying harmonics due to separation of infinitesimal in separation of a source and a sink, such that the source strength times the separation is a constant. So, that was for n is equal to 1 and m is equal to 0. For n is equal to m and n is equal to 1 and m is equal to plus or minus 1, the solutions are point dipoles separated along the x and y axis respectively. Combinations of n is equal to 1 and m is equal to plus and minus 1 will give you a point dipole separated along the x and the y axis. So, that is the interpretation for n is equal to 1. The three of them correspond to point dipoles aligned along the x, y and z directions. Okay. And for n is equal to 2, there were 5 solutions. Okay, if you recall, n is equal to 2. Okay. There were 5 solutions. Okay, 2 of them separated along the z direction. I am sorry, my apologies. Okay. 2 of them in the xy plane. Okay. 2 of them in the xy plane. Okay. This is in the horizontal plane. Okay. I am trying to plot a projection in the horizontal plane in the xy plane alone. Okay. This is corresponds to what is called phi xy. Okay. And the second one, okay, is along the axis. Okay. And this goes by the name of phi x square minus y square. Okay. Then there are 2 in the xz and the yz planes. Okay. There are 2 in the xz and the yz planes. Okay. One is in the xz plane. Okay. So, okay, in the xz plane, I will try to plot it. Okay. Okay. Positive and negative, and this is phi x z. The other one is in the yz plane. Okay, this is in the yz plane. Okay, it is not projected in the x direction. Okay. All separated by the sources are separated by distance L, and this corresponds to the function And then there is one where the sources and sinks are separated only in the x direction. And you have a sink that has double the strength at the origin. Okay. So this goes by the name of phi z square. Okay. So these are the 5 solutions, okay, corresponding to, okay, n is equal to 2. This is m is equal to plus or minus 2. Okay, combination of m is equal to plus 2 and minus 2 gives you the first one. N is equal to 2, m is equal to plus or minus 1. Sorry, this is plus or minus 2. Okay, so these are the 5 solutions. So therefore, I have given you 2 interpretations, 2 different interpretations of the spherical harmonic expansion. One in terms of separation of variable solution with homogeneous boundary conditions in the phi direction and in the theta direction, and the second in terms of superposition of sources and sinks. Okay. So next we will go on to analyzing what is called a distributed source. Okay, so what if I have, instead of a point source, I have a source that is distributed, okay, and I want to find out what is the temperature at some location x due to a volumetric distributed source, okay, due to a volumetric distributed source of source strength QV of x. Okay. The source strength here is QV of x, where QV is the heat generated per unit volume per unit time. Okay. For a volumetric source, the heat generated is per the total heat generated per unit volume per unit time, which could be a function of position in this case. Okay. The heat conduction equation in this case is K del square T plus QV, which could be a function of x. This is equal to 0. K del square T plus QV of x is equal to 0. How do I solve this? Okay. The easiest way to solve this is to consider the distributed source as a large number of point sources, okay, and I will go through the calculation of that. Okay. Okay. Divide this distributed source into a large number of infinitesimal volumes. Okay. Okay. Each volume, if I expand it out, each volume, okay, centered at the location xi, okay, centered at the location xi. Okay. The center of this is xi and the volume is delta Vi. Okay. And there is a temperature field, okay, due to that particular differential volume. The source due to that particular differential volume results in a temperature at the observation point x. Okay. Therefore, I can consider QV, okay, is equal to what is the source strength at that particular location. The source, the amount of heat generated per unit volume per unit time is, okay, QV of x, okay, of xi at that location, the value of qv at that location, okay, times the volume, okay, times the total volume gives me the amount of heat generated per unit time within that volume. Okay. The volumetric source density, volumetric source per unit volume, the source of heat per unit volume per unit time at that location multiplied by the differential volume gives me the heat generated per unit time from that volume, and I can consider that entire heat in this differential volume to be a delta function that is centered at this location. Okay. I can consider the heat in this volume to be a delta function centered at this location. Okay. Okay. And if I sum it up over all these volumes, I will get the total heat. Okay. If I sum it up over all of these volumes, I will get the total heat. Okay. And so, this distributed volumetric source I have written as a sum of a large number of delta functions, okay, and I know what is the solution for each delta function. Okay. Okay. The solution, if you recall, for each delta function is equal to qv of xi into delta vi, okay, divided by x minus xi. Okay. For pi k, let me write it again. Okay. This is the temperature at the location x due to a point source at the location xi, okay, of generating qv times delta vi heat per unit time. Okay. This is the solution for the temperature field due to this point source. Okay. Due to one of these. The total temperature is due to the sum of all of these sources, which is a sum over all I, okay, where n is the total number of differential volumes that have distributed this point source within. Okay. Okay. So, if I take the limit of delta Vi going to 0, okay, I can write the summation as an integral. Okay. I can write the summation as an integral is equal to integral dV prime, where the integral is over the location of the source. Okay. The integral is over the location of the source of q of x prime. Okay. Delta Vi times qv of xi can be written as integral over dV prime of qv of x prime, okay, divided by 4 pi k into x minus x prime, okay, integrated over the entire volume of the source, integrated over the entire volume of the distributed volumetric source, where x prime and v prime refer to the source locations and x is the location of the observation point. Okay. So, this is the temperature field due to the source at the due to the volumetric source. Okay. Temperature field at the location x due to a volumetric source. Okay. You integrate over the entire source domain of the source local source strength divided by 4 pi k into the distance between the source and the observation point. Okay. And I can also write this as integral dV prime, okay, of g of x minus x prime times qv of x prime. Okay. This is what is called a convolution integral, a function of x minus x prime times a function of x prime integrated over x prime. The integral is independent of x prime because x prime is the variable of integration, and finally the integral will just be a function of x, okay, the observation location. Okay. Once I have integrated over the source location, the temperature just becomes a function of the observation location, where the Green's function g of x minus x prime is equal to this is called the Green's function. Okay, so this is the solution for the temperature field for a distributed source obtained by just superposing a large number of point sources located at the centers of their differential volumes. Okay. So, as the volume shrinks to 0, there is no distinction between the volumetric source and the point source centered at the center of that volume. Okay. So, this is just a simple extension. Okay. And the heat flux Q is equal to minus K, okay, times the gradient of T. Okay. Note that this gradient is taken with respect to the observation location. The gradient of the temperature is taken with respect to the observation location, which is equal to minus K into Ex partial by partial x plus Ey of the temperature. Okay. X, y and z are the observation locations, and x prime, y prime and z prime are the source locations. Okay. And this derivative I had already done for you for a single point source. Okay. For a distributed point source, it is exactly the same. This is equal to integral dv prime q v of x prime into the vector x minus x prime. Okay. When I did it for a point source, the derivative with respect to x and the source location was xs, and therefore I got x minus xs in the numerator. Now I just get x minus x prime in the numerator by 4 pi into x minus x prime whole cubed. Okay, so, this is just a simple extension. Okay. So, let us use this to solve a practical problem. Okay. Okay. Let us say I had a wire, a heated wire that is generating heat, okay, a heated wire that is generating heat. Okay. Is equal to Q per unit length. Okay. Infinitesimal wire generating heat Q per unit length, and the total length of the wire is equal to 2 times L. Okay. It is plus L up to, it goes from y is equal to minus L to y is equal to plus L. Okay. And I want to find out what is the total heat, the temperature profile around this wire. Okay. Q is the heat generated per unit length. Okay. That means there is no heat generation when either x is not equal to 0 or y is not equal to 0. Okay. There is no heat generation when either x is not equal to 0 or y is not equal to 0. There is heat generation only when x is equal to 0 and y is equal, I am sorry. There is no heat generation when x is not equal to 0 or z is not equal to 0. There is heat generation only when x is equal to 0 and z is equal to 0. Okay. So, therefore, the volumetric heat source, okay, which has dimension of heat generated per unit volume per unit time, has got to be equal to Q times delta of x times delta of z, where delta of x and delta of z are volumetric, are one dimensional delta functions with dimension of 1 over length. Okay. Heat generated is Q per length, deltas have each dimensions of 1 over length. So, Q has dimension of 1 over of the heat generated per length cubed per unit time, or heat generated per unit volume per unit time. Okay. So, that is QV for this case, and to find out the temperature I just have to substitute that into this expression here. Okay. I just have to substitute, okay, QV in this expression here. Note that the source point in this case is x prime, y prime, z prime, and the observation point is x, y, z. Okay. Okay. So, QV I should strictly speaking write it as Q of z delta x of z prime delta of x prime. Okay. So, T is equal to Q by 4 pi k integral over the volume, okay, dx. Okay. Dx can go from minus infinity to infinity, integral dz from minus infinity to infinity. Okay. The y coordinate on the source goes only from minus L to plus L. Okay. Of, okay, delta of x prime. Okay. Note that these are all integrals with respect to the source point, and source point has primes in it. Okay. So, it is with respect to z prime and x prime, delta of z prime by, okay, x minus x prime square plus whole to the half. Okay. X minus x prime the whole x minus x prime the whole square to the half, okay, written in terms of components. Okay. Now, delta of x prime is non-zero only when x prime is 0, otherwise delta of x prime is equal to 0. Therefore, I can remove the delta function and the integral and just replace x prime is equal to 0 in the integrand. Okay. That is how you simplify the delta function. You remove delta and the integral and set x prime equal to 0 in the integrand. Okay. Do the same thing for the z direction. Okay. And so, this delta function times the integral will just give me the value of the integrand at x prime is equal to 0 and at z prime is equal to 0. And I am left with an integral over y of 1 over x square plus y square plus z minus z prime the whole square whole to the half power. And you can do this integral. I will not go through the details of how it is done. Okay, it's you can get it either from standard tables or you can do it by substitution. And the final result that you get is q by 4 pi k into, okay, L plus y plus root of, okay, times the natural logarithm, okay, the natural logarithm of this. Okay. So, that is the final solution, okay, for the heat generated due to a wire. Okay. So, I have got this final solution here. Now, how do I check if this is consistent? Okay. So, how do I check if this is a consistent result? Okay. I will examine in the next lecture how I will check if this is a consistent result or not, and then I will go on to discuss what happens when you have boundaries. Okay. So far what we have solved for is in an infinite domain. Okay. There are no boundaries anywhere. If there are boundaries, then what is the procedure to be adopted? So that I will discuss in the next lecture. I will see you then.